Most modern-day portable devices are powered by batteries, a device which converts chemical stored energy into electrical energy. The first battery was created by Alessandro Volta in 1800, and from constant improvements to batteries, they have been a common power source for many electronic appliances. There are many different types of batteries, each with different structures. A dry cell battery is one of the most commonly used types. The crystal cell battery is one which is expected to last a very long time, generating an abundance of electricity throughout its lifespan. Batteries are constantly being improved. This experiment aims to test a battery that is sustainable and efficient. Crystal cell batteries are made of common household chemicals, meaning they can be easily created, yet still provide enough electricity to power small devices. The crystal cell has the name crystal cell because one of its components, Epsom salt. As seen here, the Epsom salt has a crystalline structure, thus dubbing this the crystal cell battery. A large copper cylinder is cut up into 5 smaller, equal parts, 1 for the control and 4 for each of the household chemicals. For safety considerations, each of the copper rods is sanded down to avoid any sharp edges. Using a hot glue gun, each of the 5 magnesium rods are glued onto a small piece of wood. Afterwards, the magnesium rod glued to the wood is then inserted into the copper cylinder. By using the hot glue gun again, each of the components are glued together at the bottom. The chemicals used include salt substitute, borax, Epsom salt, and alum. They are then individually grinded to create a fine, powdery substance. Now that both the mixture and the outer shell of the battery are complete, the mixture is then poured in between the copper cylinder and the magnesium rod. This is done until the space between the 2 cylinders is completely full and the material is tightly packed in. After pouring the mixture in the battery should be complete. If the mixture was tightly packed into the space, the battery shouldn't need a cap, as tipping the battery over will not spill any of the chemicals. To test if the batteries work, they are being used to power a standard white LED. Just like a standard AA or AAA battery, each of these crystal cells generate 1.5 volts. Because a standard LED requires around 3 volts and 20 milliamps to power, 2 of the batteries must first be connected in series. Connecting these cells in series doubles the voltage, yet still retains the same electrical capacity or amperage. To connect 2 batteries in series, a wire must be ran between the negative of the first battery and the positive of the second battery. For more standard batteries, this could be easily done with something such as a battery case. However, as these crystal cells are not standard batteries, they must be connected using a simple means such as alligator clips and wires. Alligator clips come in many different shapes and sizes, meaning they can be used for a multitude of different connections. There's a wide selection of wire to use as well. In this case, uninsulated copper wire. This wire is cheap and very easy to work with. Red alligator clips are used for positive connections, while black is used for negative connections. The copper cylinder is a positive connection, while the negative is the magnesium rod. The connections made to the LED aren't actually that neat, but this is only a temporary setup. Most importantly, the LED or lead emitting diode does light up, meaning that the batteries work.
The mentioned test offered several interesting observations. For one, the borax turned out into a light blue color several days after testing. In addition, the powdered mixtures would occasionally become clumped together when ground in the coffee grinder. This was more prevalent when the chemicals were all mixed at once, and when mixed individually, it was visibly finer.
Overall, testing showed minimal change in the voltage generated between the 5 different batteries, ranging between 1.41 to 1.65 volts, with Epsom salt subtly proving to be the most effective. On the other hand, the amount of milliamps differed dramatically, as borax averaged nearly 40.1 milliamps, while the poorest varying chemical, salt substitute, only created a pitiful 0.01 milliamps. This difference in amperage allowed borax to prove most effective overall, since voltage multiplied by amperage equals wattage.
Many other people have already created these batteries, each having different sizes. This particular crystal cell hasn't been put in extensive testing, however the crystal cells that others have created has shown to last over 2 years, powering small devices such as a motor and an LED. One application could be a self-recharging light. For example, if going somewhere for a small amount of time such as a shed, multiple crystal cells could power a light bulb for the time needed to take whatever is needed, and after that, the crystal cells will charge back up and be ready for another use. There are many faults in this particular crystal cell battery. It's not polished up and could be better. However, as time is going on, many people are already improving these batteries to make them even better than they are now. The crystal cell battery is an intriguing form of electrical generation that offers boundless potentials for future improvements. The possibilities for self-sufficient electricity could drive further development and innovation. Thanks for watching, and this has been the effect of chemical proportions on the electrical generation of crystal cell batteries.